It really is an honor to be here and giving the Dirac lectures and getting an opportunity to talk about gravitational waves, which is one of the. It's really been an exciting time for the last few years, and I expect that by the end of this lecture series, you'll get a good sense of why we're all so excited and why we really believe this is kind of one of these transformational times in science where you witnessed the birth of an entirely new field. It's really remarkable what's happened in the last few years. So I'm going to be kind of giving the overview introduction. You'll hear a lot more from some of the other speakers. It's really an incredible, it's really an honor just to be here with these other speakers. Chung Pei is one of the experts on supermassive black holes. Hitoshi is an expert on the early universe, and Ray Weiss is an expert on the experiment I'll be talking about, LIGO, and is really one of the founders of everything we've done and has been working on this for a long time, and really he's remarkable. So I'm sure you're going to enjoy all the lectures. My goal right now is to kind of set the stage and give you some of the background of what gravitational waves are about, and what's happened in the last few years and where we might be headed. I just want to continue about Dirac just a little bit. Of course, I'm sure you're all very familiar with his many accomplishments. He's really a legend. The Dirac equation, his kind of the equation that bears his name, combined was really the first combination of quantum mechanics and relativity, special relativity in this case. If it was the combination of quantum mechanics and general relativity, then would have a theory of quantum gravity. And that's something in all the ensuing years we still haven't been able to really come up with. But this was still a big step, just getting special relativity in there. And so I really think it's worth remembering. He's had so many profound insights. And I should also mention, as I was kind of preparing for this lecture, that I found that he gave a Lindau lecture. So the Nobel laureates get together and have conferences and invite lots of people. They're really wonderful. And he attended, I guess it's the 9th one, and gave a lecture on gravitational waves specifically. And the lecture is quite interesting, as you might imagine, but he goes way beyond gravitational waves and actually talks about quantizing gravity, among other things. But if you're interested, I highly recommend you go and check it out. So it's completely appropriate that here we are, many years later, talking about gravitational waves, but now we're talking about the detection of gravitational waves and science with gravitational waves, which I think would have been pretty much inconceivable back then. Just because of the technological hurdles, and I'll touch on that a little bit as I go along. Okay, so here's my plan. There'll be 2 lectures. In the first lecture, I'm going to give an introduction to gravitational waves. Then I'll talk a little bit about gravitational wave detection. Then I'll talk about our first detection, 150914, which was incredibly exciting, and there was a lot of science associated with it. And I'll give you kind of a brief overview of that. And then I'll conclude with multi-messenger astronomy and the discovery of GW 170817. Then for lecture 2, I'll talk more about GW 170817. That really was kind of this watershed event. There's so many different things we've learned from it, and it's really impacting the future of the field. And then I'll talk about some of the very recent discoveries. We've just completed our 3rd observing run, and I'll talk about some of the exciting things that have come out of that. And then I'll end with the future and some thoughts about the future. So that's the plan. I do invite you to ask questions along the way, or at the end, or you can always just send me questions after. Okay. All right, so let's get going. GR, I'm assuming not everyone has had, a deep courses in GR and is an expert. For the purposes of these talks, GR can really be summarized in this way. And this is a saying attributed to John Wheeler, and he says, space-time tells matter how to move. Matter tells space-time how to curve. And that really encapsulates a lot of the relevant features of general relativity. It's, what's happening here is we think of space-time as kind of a fabric, and curvature of that fabric tells matter how to move. So for example, the sun curves the fabric of space-time around it, and then the Earth rolls around, if you like, on that fabric. And because of the curvature, it ends up orbiting the sun. So that's the space-time tells matter how to move. Matter tells space-time how to curve. The sun itself is the one doing the curving. Because the sun is there, it curves space-time, and now that's what causes the Earth to move. And one of the things that should be very clear is that these are coupled. So this is a nonlinear coupled set of equations, because there's space-time telling matter how to move, but the matter itself is telling space-time how to curve. That makes it a little more complicated, and that's part of why GR is not entirely trivial to solve. But so in your mind, the idea should be as matter itself causes this curvature, and then that curvature causes other matter to move in response. And that's the summary of relativity. So there are a number of things that come straight out of this picture, this curved space picture. One is that space and time are inextricably linked. You really can't separate them and talk only about space and only about time. You have to think about them together. Another thing is that, of course, matter is causing this bending of space-time, and that bending can become infinite. So as you get more and more matter, the curvature of space-time increases, and at some point it can become effectively infinitely warped, and that's what we call a black hole. And that's just a natural result of the theory. And another interesting result of the theory is that space-time can wiggle. If you imagine that sun, and if you moved it around, shook it, if you think of it kind of like a trampoline, if you're moving this object, accelerating the object, then it's going to cause waves, ripples in the surface, and those are gravitational waves. So let me talk a little bit about neutron stars and black holes, and then I'll get to gravitational waves. And this is really, I just want to give you a sense of scale, because it's easy to kind of lose track of this, and we toss these words around, but it's important, if you're going into this, just to have something in your head about what it is, how extreme these objects really are. So we'll start with the sun, and the sun is big. In the lower right here, I'm showing some of the planets, and the Earth is one of those tiny little balls there. The sun is really quite big. Okay, what you have to imagine is taking the sun and crushing the entire sun, taking the entire sun and crushing it all the way down to about the size of the city of Chicago. Okay, that's the kind of scale we're talking about. If you did that, then you would have a neutron star. And these are the densest stars in the universe. And they're the most extreme form of matter. And we'll talk more about that as we go along. Would really like to understand the properties of this matter, and that's one of the big questions in physics, and gravitational wave observations can help with that. So these are the densest stars in the universe. They're very extreme, the entire sun down to the size of a large city. Okay, but if you keep crushing, you keep pushing on that, then needless to say, you end up with a black hole. And at that point, there's a certain point where the star can't hold itself up anymore. It collapses, and essentially there's nothing left. There's just space and time, very strongly warped space and time. And that warping is so strong that you can't escape. Not even light can escape if you cross this threshold. So, one way to kind of think about it is, everyone's familiar with escape velocities, and if you could throw a ball fast enough, you could get it off the surface of the Earth, and it would just go off, flying out to space and never come back if you could throw it really fast. But for a black hole, the escape velocity is the speed of light or beyond, and you can't throw anything faster than the speed of light, and therefore nothing can escape. So you kind of already have some idea that this may be possible. What relativity does is it kind of formalizes all this. Okay. So now let's talk about gravitational waves. I've described them as ripples, in space-time. Let me give you another way to think about these. It's just good to have these kind of heuristic pictures. So one way to think about this is imagine the surface of a pond and imagine that there's a duck on the pond. If the duck is perfectly still, the surface of the pond is perfectly still. Okay? And there's no information about anything. Now, if the duck starts to move, if it starts to accelerate on the pond, it's going to send out ripples. And you can see the ripples in this picture. And the ripples emanate from the duck and go out to the very edges of the pond. And if you were there measuring those ripples, you could actually figure out where the duck is. You could figure out how fast the duck is moving. You could probably figure out how big the duck was. You can figure out all this stuff just by the pattern of ripples that the duck is emanating. And one way to think about it is the ripples are telling you that there's a duck on the pond and the duck is moving. And as the duck changes position, the ripples tell you where it's gone. Okay. So gravitational waves are exactly the same thing. Now what you do is you replace the duck with two neutron stars or two black holes going close to the speed of light orbiting each other, and you replace the surface of the pond with space-time, and otherwise it's identical. And what's happening is as these objects move in space-time, they emit ripples, and those ripples are going off to the edges of the universe, and they're informing the universe that these black holes or neutron stars are moving, changing their position, accelerating around each other. And if you can measure those ripples, you can figure out where these objects are, what their properties are, how massive they are, things like that. And so that's the idea. And you can think of it as these ripples are really the way the universe keeps track of where everything is. Even if I were to get up now and walk across the room, I've changed the gravitational field. And even in principle, the most distant galaxy needs to know I've moved a little bit because the gravity has changed just a tiny little bit. And so something has to go out. That information can't go faster than the speed of light. So something goes out at the speed of light to tell the rest of the universe that I've moved. And those are gravitational waves. So I like to say gravitational waves are the way the universe keeps track of where everything is. And they're an essential part of the theory. They were predicted by Einstein in 1917. Okay, so you can ask that, that was 100 years ago. Why did it take so long to detect gravitational waves? And so this is the other thing that's very important to keep in mind, which is the scale of what we're talking about. So gravitational waves are very weakly coupled, and we'll talk more about that as we go along. So just to get a sense, a loud gravitational wave would change. What gravitational waves do is they change relative distances, and I'll talk more about that. A loud gravitational wave changes the relative distance between us, effectively changes the relative distance between us and the next closest star, so Alpha Centauri, at 4 light years away. So that's pretty far. At the speed of light, it takes you 4 years to get there. It's as if when a strong gravitational wave comes by, it's as if it shakes that star by the width of a human hair. And we want to measure that shaking. And, that sounds hard. And a lot of people, including Einstein, said, that's not looking possible. That sort of scale to detect such tiny movements, tiny fractional movements, we don't see how that can be done. And that's a very reasonable position because that's extreme and it's not at all clear that it could be done. So how do we actually do it? Well, we built something called the Laser Interferometer Gravitational Wave Observatory, LIGO. And what these are is they're interferometers. So, what they do is they shine light down tubes to shiny mirrors, and I'll talk a little more about that. And the light goes back and forth. And there are two arms. And what you're basically doing is you're doing relative timing on the arms. And I'll talk more about that. I claim these are the most sensitive machines ever built. There's certainly some particle experimenters who might argue with me that the LHC is the most sensitive. So that's perhaps a debatable point, but I really, if you actually look at the raw sensitivity of these instruments, they're mind blowing. And let me try to give you a sense of that. Here's just another pretty picture where you can see kind of the main station, which contains the lasers and the detection, all the detection equipment. And then you can see there are these 4-kilometer long tubes, and there's just nothing in them, and then mirrors along the way. So, what is inside LIGO? What is LIGO all about? Well, it's mainly shiny mirrors. If you see the person here with the yellow glove is touching one of the mirrors, or not touching, but adjusting some aspects of the mirrors. They're extremely shiny in just, for the right wavelength. And you can see some of the vacuum equipment. So mainly it's laser, shiny mirrors, and vacuum. But then there's a lot of other stuff to keep the thing working. Needless to say, I'm a theorist and I do data analysis. I'm not an experimenter, which is why I have this kind of very heuristic view. You'll hear a lot more about all this from Ray Weiss, who's the world's expert on LIGO and the instrument itself. Here's just a video that kind of shows you the light going down each of the arms, bouncing off the mirror and coming back. And what you can do, one way to think about this is what LIGO does is it compares how long it takes light to go down each of the arms. And it's constantly doing that comparison. It's timing, doing a relative timing experiment. And if light takes longer to go down one arm than the other, then it knows that arm has gotten longer compared to the other. And it just constantly monitors that, and that's the output. Okay. The main thing here is that LIGO should absolutely blow your mind. And this is something I think that's been forgotten in the ensuing few years because it's just kind of become taken for granted. Oh yeah, we have these gravitational wave detectors and they work, and we're observing the universe with them. But the trick here is to look at the scale. So what I'm showing here is, as a function of frequency, this is the sensitivity of the LIGO instruments in O2, in the second observing run. And what's important to note is the y-axis, which is the strain noise. So this is, the level of the noise in the instrument. And you should note that it's 10 to the minus 21 or 10 to the minus 22 are the relative units. So that's 1 part in 10 to the 21. So effectively, LIGO is measuring changes in distance that these mirrors are wiggling back and forth, measuring those changes to 1,000th the size of a proton over 4 kilometers, which is incomprehensible. How is that even possible? And the short version is it shouldn't be possible. I mean, it's just that's way too sensitive. And there's so many sources of noise, and you have to worry about quantum effects on the mirrors themselves. It's crazy, but it's been done, and this is the noise curve for these instruments. And so we're now at a sensitivity that's so mind-boggling that we actually start to detect things.
Can I ask some question about this plot?
Oh yeah, please.
So for the low frequency range, is there any reason there is slight difference between the Livingston and Hanford? Like Hanford is slightly worse. It's maybe not very important, but is there any reason?
Yeah, so there are lots of different things going on in these plots. This plot is fascinating. So the low part of the plot, the low frequency part, is dominated by seismic noise. And so as you go to very low frequency, basically the Earth is shaking all the time. It's always moving. And it becomes extremely difficult to screen that out. And so for ground-based detectors, conventionally, you can't get much below 10 hertz in sensitivity, because at that point, the Earth is shaking so much that there's no way to isolate. We have these very fancy active isolation tables, very heavy, and they kind of compensate for the Earth's motion. But below 10 hertz, it's impossible. So what's happening here is, both Hanford and Livingston are in very different sites and have very different seismic properties and have different, seismic isolation instruments. I mean, they're supposed to be the same, but the properties end up being slightly different. And so there's been this, ongoing, if you like, competition between Livingston and Hanford to see which one can be most sensitive. And for O2, Livingston in general was more sensitive. And that actually also continued for O3 over a broader range of sensitivity due to various issues with actually the mirrors themselves and sight. Like, for example, one of the major things that Hanford was having trouble with, which is part of the difference here, is wind across the detector was causing, it gets very windy at Hanford, and that wind causes the whole building to shake, and that introduces noise. And so one of the things they've done more recently is introduce wind fences. They just put up a bunch of fences, a pattern of fences surrounding the detector to break up the wind so it's not laminar flow that hits the main building, and that's helped reduce the noise. But that happened after this period of O2. So that's part of the reason the noise is different.
Thank you.
Yeah. And I just, while I'm at it, I mean, there's so much information in this plot. You can see, so there's that low sensitivity rise. At high sensitivity, it also starts to rise, and that's due effectively to shot noise. You just start to run out of photons. Your laser just isn't bright enough. And so for any tiny part of time, you just don't have enough light circulating, at 1,000 hertz. So that's 1/1000th of a second. There's not enough light, not enough photons to measure the jiggling anymore. And as you go to higher and higher frequencies, that you just lose sensitivity. And then at the bottom in the middle, they're just kind of quantum noise or thermal noise. It's all the kind of aggregate noise due to the fact that you're at a level of sensitivity that every little thing that moves comes in, and you're at room temperature, and this is what you end up with. You'll also notice there's a pattern of lines. Some of these lines, like there's a very prominent 60 hertz line, and then higher modes of 60 hertz. But there are also all these additional lines, and a lot of those have to do with the way the detector is set up. And there are, for example, these violin modes where you have this mirror that you're shining the light on, but you don't want to attach that to the ground because the ground is shaking. So you actually attach it via pendulum to another mass, and then another mass, and you have these series of pendula, and they all have different, normal modes, and they kind of cancel out. And it's a very effective way to isolate. But there are fibers that attach, and those fibers can kind of ring like violin strings, and then you get these additional modes that can get rung up. So this is a very, very rich plot, which I'm going to just gloss over. But again, Ray Weiss is the person to talk to, and you'll hear from him tonight. Okay. So I'll continue. I should point out there are now 3 detectors. There are the 2 LIGO detectors, one in Hanford, Washington, one in Livingston, Louisiana, and then there's the Virgo detector in Pisa, Italy. And all 3 have been running, and all 3 have been taking data. And a lot of what I'll be talking about comes from all 3. And yeah, I just want to emphasize, there's a public talk by Ray Weiss. He's amazing. He's a great speaker, and he has such a deep knowledge of all of this. So I really encourage you to go attend his talk tonight. Okay. So I'm now going to start with the story of the first detection. So that's my background on gravitational waves. And now let me just give you a sense of, what we've actually detected and why we're all here talking about this. And that story starts with September 12th, 2015, when we first turned on the LIGO instrument. We turned on both LIGOs. We had been kind of fiddling with them and adjusting things. And then we finally kind of turned on and started to have real data streaming in and run the analysis pipelines and get going. And 2 days after we turned on, this is what we heard. And I hope this goes through. So tell me, do you hear sound? Was there any sound playing there?
There was, yes.
Okay, good. Uh-oh, now it's gone. Okay, there we go. Okay, so I'm going to play it again. Okay, and you've probably all heard this, but I think it's just, so I find it amazing that this has happened. So I'm going to play it for you again and just talk through this movie briefly. So on the x-axis is time. So this is just real time. And what I'm playing are the sounds from the two detectors. So the Hanford detector and the Livingston detector. And what you'll hear is at the beginning, you hear kind of just it sounds like white noise, like a radio when you're not tuned to a station. It's just psh, and that's just the noise. But you have to remember that that noise is at the level of 1 part to 10 to the 21. So it's really, 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 really quiet. But to us, it's loud because that's, right at the range where we're trying to be sensitive. So there's that noise, and then you'll hear a thump. And what I'm showing here, this is kind of a visual way to see the sound. And so what I'm showing is this is a plot of frequency on the y-axis, and how bright the dot, how bright the picture is a sign of how much energy there is at that frequency at that particular time. And so what you'll see is you'll see it arc up, and that's telling you that it's going to higher and higher frequency with time. And it's going to get brighter and brighter. That's telling you it's getting louder and louder with time. And so that's kind of a visual way to see what you'll hear, which is what we call the chirp. And that chirp is two black holes getting closer and closer and eventually colliding. And we'll talk more about that process. What it'll do is it'll play the actual data. I've amplified it a lot, and I've turned it from gravitational waves into sound. So just to be clear, gravitational waves are not sound, they're ripples in space-time. But because they're in the same frequency as what you hear, it's convenient to talk about them as if they're sound. And I can talk more about that analogy down the road. So what you'll see and what you'll hear is this chirp. I'll play it twice, and then I'm going to shift it to higher frequency because our hearing at the low frequencies at which this object was detected isn't as good. So I'll switch it to higher frequency, and then you'll be able to hear it better. That's just so that you can hear it, to guide your ear, as it were. Okay, here we go. Okay, so that sound, that thump, or the whoop, that's the detection of gravitational waves. If you were looking, you could see it was happening in both detectors simultaneously. And what we could do was analyze that chirp and figure out what it was. And so that's what we did. And we inferred that it's a merger of two black holes, that each black hole was 30 solar masses, so 30 times the mass of the sun, that the system was about 40 megaparsecs away, 400 megaparsecs away. And for a fraction of a second, this event emitted more energy than all the stars in the universe combined. And that last thing, let me just say that again, because that's kind of mind-blowing. And it's one of the things about this field. Again, everything is so extreme. So there's energy being radiated in gravitational waves. So there's some amount of power. And the power of this system as it merges for this fraction of a second, say the last tenth of a second, that amount of power is more than if you took all the stars in the entire observable universe, all the light coming from those stars, and added it all up. It would be less by a significant fraction than the amount of power from this one binary black hole collision. This is extraordinarily luminous, but everything that's coming off, all the energy is in gravitational waves. And gravitational waves couple very weakly with matter and with everything, and they kind of pass through everything. And so it's very hard for us to detect. So that's why it took us 100 years, because it has this tiny effect. It also means that the gravitational waves are very pure, because they don't couple with any matter, it doesn't matter what's, as it were, along the way. Whatever is there, if there's a galaxy there, it goes right through it. It doesn't even notice. And so the gravitational waves that we measure are pristine. They're very accurate representation of what was emitted. And so by analyzing them, we learn a lot. And that's part of the story. And I'm just going to show, I mean, this is the canonical plot. People have tattooed this onto their bodies. It's a really amazing plot, which is just, this is kind of our discovery plot. It shows the data in Hanford and Livingston. And you can see kind of the raw data, and off to the left, it's kind of bouncing up and down. And then if you look carefully, you can see that it starts to get faster and faster and louder, and then it suddenly stops as the black holes merge and then rings down. It was also important because this was a first discovery. We wanted to be really confident. And so it was very important to us that we see it in two instruments. And so here you can see the Hanford and Livingston data on top of each other in the bottom plot. And the fact that they measured the same signal gave us extra confidence that what we saw was real.
Dan, we have a question from Jeremiah Murphy.
Oh, great. Yeah, hi, Jeremiah. Go ahead.
Hey, Dan, how you doing? I just had a quick question. That video you showed with the chirp going up, I've heard that video many times. This time I heard something different. And I'm wondering if there was something new, or if it was what was coming across on Zoom. I heard two different octaves. The first time it played, I heard a low octave chirp, and then I heard a higher octave chirp. Was that Zoom, or was that on purpose?
No, that's on purpose. So what we're doing in that video is, it repeats, if you like, 4 times. And the first 2 times is just what we really detected. And that's the real frequency of 150914. The second time, we've just shifted it up in frequency just so you can better hear the chirp.
Yeah.
We just want people to be able to hear that whoop. So that's not what we detect. It's just shifted. It's kind of the same thing you do with images, where you kind of change the color scale. Here we kind of shifted it so that you could hear it better. So that's all. But otherwise, we kept everything the same. We just shifted it up by, I think, a few hundred hertz, something like that.
Okay.
So I mean, it's so you've probably only heard the low frequency thump. And that really is what we heard. But it's so fast that people don't get the sense that it's really sweeping up in frequency. And so the hope was by shifting it up, you would hear that better. Yeah. But sorry, it's confusing. And I'll play another sound as we go along that's much higher frequency, and I don't have to do any messing with it. So that's coming up. Okay. All right. So Jeremiah, does that answer your question?
Yeah, exactly. That's what I suspected. Thanks.
Yeah, great. All right. So I think it's helpful. I'm just going to spend a couple more slides on this event, and then we'll move on to other things. I think it's helpful in general when we're talking about gravitational waves. What we're detecting so far are binary coalescences, what we call CBCs, compact binary coalescence. And we break this down into 3 general phases. There's the in-spiral phase, where you have 2 compact, it could be neutron stars or black holes, they're just orbiting each other. And as they orbit, they're emitting gravitational waves. And if they emit gravitational waves, they lose energy. And that causes them to in-spiral a little bit, get a little closer because they've lost energy. If they're closer, they have to go faster. That's just Kepler's laws. So now they're going faster. If they're going faster, they radiate even more energy. And so they come in a little closer. Now they're going even faster, okay, which means they're radiating even more energy. And if you think about it, that's exactly the chirp. What's happening is you're going faster and faster and getting louder and louder. And that happens until the merger stage, where the black holes effectively touch. At some point, you go from 2 black holes or neutron stars. The neutron stars will just crash into each other. The black holes kind of envelop each other and form a bigger black hole. If you're only talking about black holes, then you have this bigger black hole, and then it is very perturbed because it's just been formed by 2 smaller black holes crashing into each other very fast at close to the speed of light. And then it black holes don't like to be perturbed. That's one of the rules about black holes from general relativity. So it rapidly, what we call rings down, it rapidly becomes a sphere, and it does that by oscillating, emitting more gravitational waves, and ending up as the most perfect sphere in the universe, assuming it's not spinning. So that's the process. And so we split into in-spiral, merger, and ring down. The in-spiral part is this chirping part. It ends at merger, and then there's a very quick ring down kind of thump. And that's what we detected with 150914. We had this very clear signal that matched these predictions extremely well. So this is a plot that you don't often see, and I think it's probably one of the most interesting plots in all of gravitational wave astronomy so far. And so I'm just going to spend just a little bit of time on this. So what this plot is showing is the data in our two detectors as a function of time. So this is just the strain, this fractional change in distance as a function of time. And so you have the data, and then we have the best fit to the data, which is this kind of light blue, the cyan band. So that's, you analyze the data, you say, we think there's some black holes there. What are the parameters of the black holes? You find the best fit. They're like 30 solar masses each, and you do put that in, and then you get this light blue band, which matches the data quite well, both detectors quite well, and you can see that here. Now, what I'm also showing here is what we call the wavelet analysis, which doesn't know anything about relativity. So this is just saying, I know what the noise looks like, and then there appears to be excess power over the noise, and I'm going to fit that power to wavelets. So I don't know anything. I'm just going to kind of fit it to a bunch of random little oscillations and see what comes out. And when you do that, you get the dark blue curve. Okay, so that's no general relativity. So the dark blue curve is what is in the data. The light blue curve is what was predicted to be in the data from general relativity 100 years ago. Okay, those predictions are gravitational waves exist, general relativity is correct, black holes exist. We're going to assume black holes have the properties predicted by general relativity. We're going to put all that stuff on a supercomputer. We're going to run it. We're going to look at the gravitational waves come out, and we're going to make a prediction. And that prediction is the light blue curve. Then the dark blue is, this is what we detected. And what's absolutely remarkable is that they match. So I view this as one of the most stunning, confirmations of theory ever, because black holes are truly extreme. Gravitational waves are, very minuscule and have never been directly detected. And here we are, everything just fits. And this is just, science, when it works, it's phenomenal. And this is, not to be taken for granted. It could have been anything. Our theories easily could have been wrong. And yet here we have that everything match.
Sorry, Daniel, one quick question. So how many parameters do you need for the binary black hole template? So do you extract do you feed to the masses, the spin, something like that?
Yeah, that's right. So in theory, a binary black hole merger on the sky has 16 parameters. In practice, we don't fit for all 16. So for example, in this particular case, we assumed the black holes at first were non-spinning. Just to simplify things, we assumed that it was a circular binary. And then, that lets us make, that lets us reduce the parameter space down to something like 7 parameters. And then we can do the fits with those 7 parameters. We then go back and the part of this has to do with the way the data analysis works. It's looking in a full 16-dimensional space. Trying to match this in 16 dimensions is very, very expensive. And if we did that, we'd have a very hard time ever converging. So we have to reduce the dimensionality, especially in the searches, and search for anything that kind of looks like this. We'll just assume there's no spin, and then we can add spin and see if that fits better. And so for this, it was, I believe it was 6 or 7 parameters, something like that. I can go back and check.
How about the other wavelet? There are parameters.
So
right?
the wavelet, yeah. So the wavelets. So that's something where it's a question of how many wavelet families, how many wavelets you allow. And in this case, actually, the wavelets, I think it was something again like 16. I think maybe it was 15. I think it's 3 parameters for each wavelet, and then there were 5 of them allowed. But that you could have more or less, and then there's an Occam factor. If you're adding more, does it really fit the data that well? And you end up with something like 15 parameters. Mm-hmm. So in fact, for this analysis, the wavelet fit has more degrees of freedom than the gravitational wave fit, which in some, kind of makes sense because, theory kind of constrains what's possible. And for some of the data I'll show, as you go along, now we've been refining what we call our waveform approximants. The process of doing this detection, finding the source and then doing parameter estimation to figure out what the source is, that's a very long, involved process. There are lots of nuances there, which I'm happy to talk about. And as we've been going along, when we do this, we don't use direct numerical relativity because we do a Markov chain Monte Carlo. So we're going around this high dimensional parameter space, and we can't run a supercomputer simulation as we do that. So we have to use what are called waveform approximants, black boxes that mimic what the gravitational waveforms are. That's what we're using here. And we've been refining those approximants. And so more recently, we're using much more sophisticated approximants that have many more parameters in them. And for example, allow for 2 spins misaligned arbitrarily. And that's a much more complicated problem. You get much more, it's a very rich set of waveforms when you do that. But we're needing to incorporate that now because the data is forcing us to, which of course is extremely exciting. It means the data is quite rich. So I'll talk more about that probably in the next lecture. But that's an excellent question. Okay, so I'll continue, but again, just remember this, this is basically an Einstein was right type of plot. The prediction from over 100 years ago matches the data, and that's phenomenal. And so are they really black holes? Yes, they are. So there's a whole field of study, which I'm gonna kind of gloss over for these lectures, which has to do with the astrophysics, the formation astrophysics. One of the most interesting questions you can ask is, how does the universe make 2 30 solar mass black holes that merge? And that ends up being a very tricky question. And they have to merge, in the more recent universe so that we detect it. And so there's an incredible amount of astrophysics and science that goes into this. There are different models, and this is very rich right now. There are a lot of arguments in this field. I'm just showing a picture of one of the models that I've been working on, which is called the isolated or field model, where you start with 2 stars in a binary, and each star goes through its evolution and then explodes in a supernova and forms a black hole at the end. You end up with 2 black holes near each other, and they eventually merge. There's a lot of knobs. There's a lot of tricky science going on here. There's this phase called the common envelope, which you can see towards the bottom. It's that purple blob where now you have a black hole orbiting basically inside the other star, and the details of how that works, not fully understood and are crucial to whether or not you end up with 2 black holes that merge. A lot of interesting science here. I'm going to kind of put all that aside for now, but if there are questions, we can come back to that. And tomorrow, in the next lecture on Wednesday, I'll spend a little time revisiting this. It's become particularly exciting and interesting as of late. And I should say, there are lots of experts on the faculty about explosions and transients and the details of how this all works and the different parts here. much more expert than I am. And so, you know, they should jump in if there are questions about all of this. Okay. So this was a major big deal. It was the first direct detection of gravitational waves and the first direct detection of black holes. And so needless to say, as you all know, essentially the founders of this field were awarded the Nobel Prize, and you'll be hearing from Ray tonight. He's the one on the left. And so, you know, it really, this is one of these things where, you know, the prize was awarded quite quickly. I don't think anyone was surprised. It's amazing. This whole story is amazing. Okay. So I probably have, how much longer should I go? I have about 10 minutes or so, is that right?
So this session lasts another half hour, so you have plenty of time if you want to go, but at your own pace.
Okay, great. So I'll just, you know, if I go the full half hour, then there won't be time for questions. So I'll probably shoot for another 15 minutes or so in case people are holding questions to the end. So that was just the prelude. That was just the very beginning. That was our first discovery. Now I'm going to go on to, there were a number of other black hole discoveries. We ended up with, you know, something like, I mean, there were a few in the first observing run, and by the end of the second observing run, we had 10. And now we have many, many more, and I'll talk about those. But there was one event that happened in the second observing run, which is worth spending some time on, and so I'll do that now. So the stage is now set. I'm not going to tell you about the event that happened on August 17, 2017. And now I'm showing you a plot of that. This is kind of the visual representation again, time and frequency, and you can see this arc off to the right. It's very clear arc. And if you kind of defocus your eyes a little bit, you might even see the evidence that that arc is going off to the left at low frequency, not as loud, but that there's a long chirp there. So we detected this in Hanford on August 17, 2017, and that's pretty exciting. That is not what the noise looks like. There's clearly a signal there. So that's phenomenal. But we didn't detect it at Livingston. And the question was, you know, why? Our automated systems said there's nothing at Livingston. And actually, a UChicago postdoc, Reed Essick, went and looked at the Livingston data and saw this. And what you see there is this incredibly loud event. You can see that kind of triangular looking thing is an incredibly loud event at Livingston. But that is not a track. That's not one of these in-spiral things. There's no chirp there. That is just a kind of bong, extremely loud, completely dwarfing everything. And that's, you know, we have a very technical name for that. We call it a glitch. That's our term. And that's something that just happens. Our detector is so sensitive, every now and then something shifts a little bit, and it causes this incredibly loud glitch in the data. Okay, so that's why Livingston was like, well, there was a loud glitch. I have no idea what was there. The data is no good. But you know, Reed immediately noticed, as you may have noticed, that there's actually this beautiful track underneath the glitch. And that's very encouraging. And so you can remove the glitch and what we call mask out the glitch and see what's left behind. And when you do that, this is what you get. And this is the sort of thing which in the gravitational wave community you dream about. I dreamt about having a perfect detection like this, a long, long track. The fact that the track is long means it's very, very low mass. And I'll talk more about that. This beautiful track in Livingston. And it must be said that that track alone, just that track in this one detector, is one of the loudest things we've ever detected in gravitational waves. Just that track. So it's incredibly loud. It's incredibly beautiful. What was weird is we didn't detect anything in Virgo. So there's Virgo, nothing there. And that's, a little odd, but, that's what happens. Virgo is less sensitive. But, this thing was so loud at Hanford and Livingston, it's a little surprising that nothing was seen in Virgo. I'm going to skip this. This is just to argue that Virgo was running. What's interesting is that the fact that we didn't detect anything at Virgo was actually a gift. I mean, Virgo is less sensitive anyway, but for it not to detect it at all was a sign that this must be somewhere on the sky where Virgo is not sensitive. And so that's what we find. And that let us figure out that, in effect, the location. So I'm now showing the Virgo beam pattern. So this is where is Virgo most sensitive and where is Virgo least sensitive. And those dark blue spots are where Virgo is least sensitive. This event must have happened near one of those spots. That's why Virgo didn't see it. So the fact that Virgo didn't detect it helped us figure out where the source was on the sky. And I can talk a lot more about that. Okay, so this is the key thing. What did we hear? So here are some other events that we had detected. And at the top is 150914. And what I'm showing you now is in time, the waveform. This is the best fit waveform. And what we detected in band. So for 150914, it lasted about a quarter of a second. And you can see it was quite loud. We had a few oscillations, maybe 7 or 8 oscillations, and then it merged and went away. And then we've detected some other events. The ones like 151226 had more oscillations. That means it merged at higher frequency. And if you think about it, higher frequency means lower mass. If you're really big, if you have 2 big black holes and they merge at low frequency because they kind of touch early, if you like. If you have smaller black holes, they can get in closer and closer and they end up merging at higher frequency. So the farther you go to the right on this, the lower your mass. Okay, I'm now going to play you 170817. So you're going to see the waveform. This is what we detected. And that's what we saw in those trips. I'm now going to play it for you with sound. So there it goes. So what you can probably already tell, this is different from the other events. This one goes on longer. It's in our detector for quite a while. So I'm playing this in real time and you can't even see the oscillations, but it's just oscillating and oscillating and going to higher and higher frequency. It's now at hundreds of hertz. And depending on your speakers, you might be able to start to hear it. You should start hearing a hum. And because I don't have access to my mouse, I can't jump ahead. So we're gonna have to listen to the whole thing. It lasts about a minute. You should be able to hear that hum going to higher and higher frequency now. This is the objects getting closer and closer and going around each other faster and faster. Okay, so that was what we heard on 170817, and it was really loud. I mean, if you had your volume up, I mean, you can really hear that. It's unmistakable. And from a data analysis perspective, this thing was absolutely unmistakable. It was the loudest thing even to date that we've ever heard. And it's just different from everything else. It's at very high frequency that corresponds to very low mass. And in fact, the mass is extraordinarily suggestive. So what I'm plotting here are the blue things are a bunch of LIGO Virgo black holes that we've detected. We've detected many more now. This is a slightly old plot. And below that, there are the neutron stars, the yellow dots. Those are known neutron stars whose masses we've detected for other reasons, in other ways. And now let me show you where the masses are of what we detected with 170817. They're right there, right smack in the middle of all the neutron stars. Okay, so that the circumstantial evidence from that is that we had detected a binary neutron star system, and that's extremely exciting. That's a whole new class of system. Because they're neutron stars, there's the hope to detect light. And so that's the next part of the story. So when black holes are black, they don't emit any light, nothing comes out. So you can't see them. So if you take 2 black holes and you merge them, even though I've argued they're unbelievably luminous, their amount of power is, astronomical, literally, but it's all in gravitational waves. There may be no photons at all. It's totally dark. If you point your telescope, you may not see anything. But with neutron stars, there's a lot of matter. Neutron stars are the densest matter. Remember, you can think of this as taking the entire sun, squeezing it down to about the size of Chicago, but that's the whole sun in there. You're taking two of these and you're crashing them into each other. That's gonna, that's likely to produce fireworks. And so there's some hope of seeing something. And in fact, that's the next part of the story. Okay, so what I'm going to do now is show on the bottom the gravitational wave detection. So it's the familiar, this is just time in the x-axis. In the bottom panel, this is gravitational waves, and it's the frequency plot, and you'll see how bright it is. It's the plot you've already seen. In the top, I'm showing as a function of time, lined up, the gamma rays that were detected by the Fermi satellite. Okay, here we go. Okay, that ding was a burst of gamma rays. So about 2 seconds after the gravitational waves merged, there was a burst of gamma rays. And that was a detection. And so not only did Fermi see it, but Integral, another instrument, saw it. Fermi saw it in different bands. It's a very firm detection. So there was definitely a burst of gamma rays 2 seconds after. And that's extremely exciting. There have been predictions that short gamma ray bursts, of which this was one, might be formed by binary neutron star collisions. Now we detected a binary neutron star, and 2 seconds later we detected gamma rays. It's phenomenal. Okay, and there are arguments that show that they're associated. I won't go into that. The gamma ray burst itself is fascinating because it was very low luminosity. We think that's because we didn't see it face on. That's a whole other story. It's absolutely, there's a lot of activity there. I'm going to skip that. You can ask me about it later. I'm just going to kind of wrap up this lecture with the next part, which is, okay, we got gravitational waves, we got a gamma ray burst. What else? Now, if you have two neutron stars and they collide, that's an incredible amount of energy. All that matter gets extremely hot. There's predictions that things would happen, and in fact, that there should be something called a kilonova, and we would love to see that. And so you might remember that Virgo saw nothing. That helped us isolate to some smaller region of the sky where this might be. We could go look to see if there was anything there. And a lot of people did that. I was part of a team that did that. I'm just going to give you a little sense of this. Which was we used the dark energy camera, which is a camera meant to do other things. And we kind of co-opted it and said, we have something really exciting. Please let us go point at this part of the sky. And we did. There are a lot of details here. I'm going to skip over those just to say this dark energy camera looks at a large part of the sky. Those are CCDs you see in the left. Each of those little things is like a CCD that you would have in your camera, only it's a very big CCD, and it's extraordinarily sensitive. And this camera has a lot of those and takes pictures of a lot of the sky. And so we took all these snapshots and then could look for anything that's changing. And sure enough, we found, as did a number of other teams, we all discovered this object changing. And I don't know if you can see it. There's a galaxy at the center. And if you look just up and to the left, you'll see that there's a star that appears and then fades away. And that is exactly what was predicted. That's a kilonova. And that, we believe, is associated with this source. And so here, for example, is, some, on the left is kind of what our discovery, some composition of our discovery images. And then on the right is what happened 14 days later. So this thing came up, was very bright, and then, faded away. And this is a big deal because not only did we hear in gravitational waves the source, but now we saw it in light. We saw it in gamma rays, we saw it in optical, we saw it in infrared, and then eventually we also saw it in radio. We saw it across the whole band. Okay. So there's a lot more I can say about that discovery and all the different things we've learned from it, and I'll touch on some of those things in the next lecture. But the first thing, just to take away from this, is that this is the birth of what we call gravitational wave multi-messenger astronomy. So we have gravitational waves and we have electromagnetic waves, and that combination, gravitational waves and light, lets us learn things that we could never learn from either separately. The gravitational waves are really being sourced by the motion of the matter, the curvature of space-time. And so you really look into the heart of the event. You can see that there are two neutron stars there. You can measure the masses. You might get information about the inclination or spins or anything else. So you really see into the heart of the system. And then the light, so right now what the movie is showing is those gravitational waves kind of coming off the system. And then the light tells you about everything that happens after. And what's being shown here is the kilonova. The gamma ray burst was that yellow jet. And then this thing, this cap that turns blue, is a visualization of the radio that comes off of this. And all of those are telling you about the system, the astrophysics of the system, the astrophysics of the environment. There's an incredible amount of information here. It really is a gold mine. And that's one of the things we've learned from this system is where all the gold in the universe is made. And I'll be able to talk more about that in the next lecture. So I think what I'll do, so I think what I'll do is I'll stop here. And then in the next lecture, I'll pick up and I'll talk about some of the things we've learned from this particular discovery, this one discovery. And then I'll go on to some of the more recent things we've learned about, sources, from our data from the third observing run. So I'll end there, and we have a few minutes for questions.
Right. Great. Thank you so much, Daniel. It's just amazing. So if people have questions, they can raise their hands in the participants list, or I've seen a bunch of people join the Slack channel. One question to just start things off is, what is the significance of that 2-second delay in the gamma rays?
Right. So that's a fascinating question. So we had the gravitational waves, the object merged, and then there was this pause, and then the gamma rays came through our instrument. And one of the things I'll talk about next time is the way we use this to measure, if you like, the speed of gravity, or speed of light, depending on how you think about it, just that photons and gravitational waves travel at the same speed. I'll spend time on that in the next lecture, but for now you can just ask, why is there a pause? And the point here is that, what we think happens is you have these neutron stars, they merge, but it takes a while for the jet to form and for it to shock. We think what happens is you form a jet, the material starts jetting out, and then there are shocks. And those shocks are what are generating the gamma rays. And this is all a very high Lorentz factor. And when you kind of work through all that, there's a pause. And that pause can take, a couple of seconds. And so the story is that that's what happened. The shocking mechanism takes a couple of seconds. So there's a slight delay before the gamma ray burst happens. And then the rest of the stuff, the kilonova, which came up, we think in hours. Our first images are something like 12 hours after the event. So exactly when that first got bright, we don't know, but we think it's on the order of hours. And that's what you're seeing right now in the video. That's just how long it takes for that radioactive material to start emitting, enough light that we can see it. And so that's the story. It all kind of fits, but it's very interesting. And there's a lot of information in that delay. And as we detect more of these things, we'll get the distribution of those delays. And then we'll be able to really start, characterizing this this is relativistic astrophysics, extreme relativistic astrophysics. We'll be able to characterize that and learn about it. And that's something people are very interested in.
We have a question from Efrain.
Yeah, so my question was, for my understanding, since the detectors went live, we've been detecting a lot more events than was originally expected. My question is, do you have to take into account interference between events, or are there just still not enough events to have to worry about interference?
Right. Okay. Great question. So the first part, this issue of whether we're detecting more events than we expected, I think that must depend a lot on whom you talk with. There were quite a number of papers saying, predicting rates that might be around what we're detecting. There's a wide range of predictions. I think it's fair to say that at least for the binary black holes, the rates are not troubling. They kind of fit into various theories reasonably comfortably. That's not as true for binary neutron stars. The fact that we detected this event, 170817, so early in our observing is maybe somewhat of a puzzle. And so rates are very interesting, and it's one of the primary sort of astrophysical products of LIGO. The first thing we can tell you is how often do these systems merge, and so that's one of our key points, and the theorists have to match those predictions. So now the question of interference is very interesting, and so one way to think about this is these events like 150914 and even this event 170817. This one lasted a long time by our standards. It lasted a minute in our detector. And so the interference you might think about, that comes into play if we're detecting events more frequently than one a minute. As a rough benchmark, we probably detected something like 50 events in 03 over the course of a year. And so the probability of having two events within the same minute are pretty low. But it's actually even more fine than that, because even if we had two events overlapping, what we really care about is the time of the merger. And we measure that to a fraction of a second. We're at kilohertz sensitivity. So, roughly speaking, you can think of it as 100 to 1,000 of a second is how well we measure events. And as long as we don't have two events merging in the same thousandth of a second, we can pull them apart. And so we need a fairly high event rate to have it be completely, to have what we call confusion noise. Okay. So not something we worry about as much. I mean, that'll be a wonderful problem to have when we have so many events. However, as we go to high redshift, our sensitivity goes down, and then our ability to tell these events apart goes down. And eventually we end up in a regime where we can't tell them apart, and there's a background hum from all the events in the universe. And that's what we call the stochastic background, the astrophysical stochastic background. And that hum is fascinating because it tells us it's a kind of an integrated measure of all the binaries in the universe. We haven't detected it yet. And the fact that we haven't detected it yet is itself interesting because it limits the number of systems at high redshift. And that's something I'll talk about in the next lecture. And so there is, exactly as you surmise, there is this kind of background hum, and that's something that's important, we believe is out there, and hopefully we'll detect soon. Just as a final addendum, in addition to the astrophysical background hum, we believe there's a cosmological background hum of gravitational waves due to the Big Bang itself. In the same way that there's the cosmic microwave background, where that's kind of the baby picture, the earliest picture of the universe, you can go even earlier, and there's the equivalent in gravitational waves. And that's something we would love to detect, the gravitational waves from the Big Bang or inflation or whatever happened in the first fraction of a second of the universe. That's not something that we've detected. That's not something that we expect LIGO to be able to detect. So that'll probably take a while. But there are instruments that are specifically being designed to look for that, and that will be a phenomenal discovery if it ever happens.
We have another question from Pablo.
Hi, thank you. I actually had one of my questions was about the gravitational background, like the microwave background. So thank you that you addressed that already. The other two things that I wanted to ask is the remnant of the neutron star merger, it is still emitting something in electromagnetic spectrum, or is completely dark?
So for a long time, it was actually getting brighter. And then the last things we've been detecting on radio as it faded away. And I believe now it's completely dark and we haven't detected anything further. But to be honest, I'm not 100% sure. So if anyone else knows, they should chime in. But I believe it's now got faded completely away and we haven't detected any more photons at all. But for months afterwards, there was still some radio emission. And that was used to make very interesting, for example, there were arguments that you could use it to constrain the inclination angle. It's really very, very interesting what's possible with the radio, because you can get very accurate measurements. But I think now it's completely gone.
Thank you, awesome. And my second question was maybe very silly, but what sensitivity you will need to have in order to detect gravitational waves from like local things like Jupiter orbiting the sun?
Yeah, so the problem with Jupiter orbiting the sun, sorry, I'm talking about noise, there's something outside. So there are two questions to ask, for any potential source. One is how loud is it? And the other is what frequency is it? So for Jupiter orbiting the sun, the gravitational waves are first occurring at the frequency at which Jupiter orbits the sun, which is, I actually don't know, but many, many years. And so you would need a detector that's extremely low frequency to have any hope. And as I said, for LIGO, unless it's orbiting the sun, at least, the year has to be at least 10 seconds, shorter than 10 seconds, because at 10 hertz, the seismic noise wipes us out. So for LIGO, we have no hope. And for most sources, we have no hope. We're not sensitive. But the other thing is how loud it has to be. And remember, when I say 1.10 to the 21, that's for very loud sources. And, a rough figure of merit is to be very loud, you have to have a very dense object accelerating so that over the period that's relevant, which is the frequencies we're sensitive to, on the order of a second, over that period, it has to be equivalent to accelerating to close the speed of light. So when you have two black holes orbiting each other, you can think of it as one black hole is going this way, and over a fraction of a second, 1/100th of a second, we've turned it around and now it's going close to the speed of light in the opposite direction. And that's why the power is so, astronomical. Jupiter is not really doing anything close to relativistic, orbits. So the gravitational waves are extraordinarily weak. And so even if we would have to go to space to get to low enough frequencies to measure Jupiter, even then, it's very hard to imagine something that could detect that.
Of course.
So unfortunately, maybe in the far future, but
no, I don't think that's possible. Your answer is perfect. Thank you very much.
Yeah.
I have a related question. So very naive question, but is single object actually generate gravitational waves? We need a quadrupole, right? So, supernova, core collapse supernova probably doesn't emit detectable gravitational waves. So does actually Jupiter can, in principle, generate a detectable gravitational wave?
Right. So that's a great question. So for Jupiter to have a gravitational wave, it would be Jupiter going around the sun would generate gravitational waves. But Jupiter itself, just sitting there, there's nothing accelerating. So no gravitational waves.
Okay.
Now, supernovae is a very interesting question. So you're absolutely right. To generate gravitational waves, you need a time-changing quadrupole moment. And if you think back to my analogy of the pond, or what gravitational waves are, is they tell you that the gravity is changing. If you have an object and it just changes spherically, like if our sun just gets a little, the radius shrinks, then if you like, because of Gauss's law, if you're far away, nothing changes, right? If you even do the Newtonian calculation, the force of gravity isn't going to change. If the sun right now got much smaller, the Earth would still go around the sun exactly the same. It would still take a year. That means that since the gravitational field hasn't changed, there's nothing to update. No gravitational waves are emitted. And so a supernova, if it's perfectly spherical, emits no gravitational waves. But for core collapse supernovae, we think it's probably not perfectly spherical. And so, there's lots of evidence for asymmetries. You can look at 1987A, like those, you get these rings and all this stuff. So in general, we think supernovae probably aren't perfectly spherical. And if they're aspherical, then we can hope to measure the gravitational waves. But exactly how aspherical they are, we don't know. And so we have to wait for a nearby supernova to go off. And by nearby, we mean at least in our galaxy, if not on our side of the galaxy nearby. And if that happens, we think it's extremely likely we will detect gravitational waves. And that will teach us an incredible amount about the very heart, the engine of the supernova. So that's something we're really excited about. But the supernova rate is like 1 every 50 or 100 years. So we have to be patient. And so whether or not that's going to happen in our lifetimes, we have no idea. It could happen tomorrow. That would be terrible because the gravitational wave detectors are off right now. But if it happens in 2 years, that would be wonderful. We'll have nice sensitive detectors, and we have some hope of detecting it and learning about supernova physics. So we just have to wait and see.
And you'll probably also detect neutrinos, so making it really, truly multi-messenger, right?
Exactly. And so the neutrinos, in fact, we think the neutrinos will be, the first thing. We're very confident we'll detect neutrinos, and then we'd have neutrinos, would have gravitational waves, and would have light. And it would be a triple detection. That would be the greatest thing. So that's kind of the dream scenario for astronomy for the coming years, but we just don't know when that's going to happen. And it could be, 100 years, or it could be happening right now. We just don't know.
Can I make a
give a comment on that.
Oh, sorry.
I was just going to say, I've done those calculations on how much gravitational wave you would get from a core collapse supernova. And I'll just give you the numbers. With the current sensitivity, LIGO would be able to detect a core collapse supernova out to about 3 kiloparsecs, given current theories of what those aspherical motions are. And for context, the galaxy is of order 100 kiloparsecs across. So that rate of 1 for every 50 to 100 years is for a galaxy-sized survey. But given the current detections, we really could only detect core collapse supernovae out to like 3 or 10 kiloparsecs at best.
Yeah, it's not looking good. The most optimistic theories I've heard put the distance at 2 megaparsecs. But I think those are really taking liberties in their supernova physics. So I agree. I mean, this is not something I'm holding my breath for, but we'll see. You never know. It'll happen eventually. That's for sure.
Yeah, right.
The only question is how long. And when it happens, it'll be spectacular, but it could be a while.
Yeah.
So we're sort of at the end of the time that we have scheduled for this session. So depending, Dan, how your energy is holding up, I'm sure people would be happy to continue to ask you questions. I do want to drop in the chat the link to the information about the public talk tonight with Ray Weiss. So everyone, if you can make it, that would be great. The registration information is available at that link. So Dan, it's up to you basically. If you want to quit now and pick up things.
One question in the.
Okay. Or there is a question in the chat.
Yeah.
Okay. Why don't I'm happy to take a couple more questions. And I just wanted to reiterate, I would really encourage you to attend Ray Weiss's lecture. I mean, he's amazing.
Okay, my question is, how do you distinguish the merger between two neutron star as opposed to a merger between a neutron star and, let's say, a more speculative axion star or two axion stars?
Yeah, so that's a great question. It's sort of, how do we know what the objects are that are merging? Mm-hmm. And so, the first thing we measure is the masses. And we, depending on the system, we either measure the mass, the total mass or the chirp mass, and there's something. But we measure the masses, and we get some insight into the mass ratio as well. So usually we get, the masses of the objects. But for the most part, so far in the signals we've detected, those masses, they could be black holes, they could be neutron stars, they could be quark stars or some extremely exotic thing. It's very hard for us to tell the difference. As long as, the sizes, especially for the more massive objects, the sizes have to be on the order of the horizon size of the black holes. They can't be big and puffy because we measure them orbiting out to just about when the horizons touch. So for the binary black holes, those objects have got to be, horizon scale objects. So if you have a theory that produces a horizon scale object, it's very hard for us to rule it out. Now, even there, it's getting more difficult because we're starting to see ring down from these objects. So not only do you need now a theory that has horizon size objects, but then it also has to have something that kind of oscillates and rings down and goes away completely on the timescales predicted by general relativity for black holes, which are pretty short. So that's not so easy to do with matter, but that's kind of what we measure. For the neutron star case, for the low mass case, we don't have as much information because they actually merge out of our frequency band. So we don't actually see the merger. We measure the chirp, but the final chirp happens out of our band. And so it's very hard for us to tell whether those objects are black holes or even neutron stars, distinguishing those. And so what we look for is as they get closer and closer, and you can see it in the movie, though maybe the movie doesn't depict this as well. As they get closer and closer, the gravitational field from one, it exerts a tidal field on the other object and it starts to squeeze. So both neutron stars are starting to get squeezed. And the amount they get squeezed is a very sensitive function of the equation of state of the neutron star. And so black holes, for example, don't get squeezed at all. Neutron stars get squeezed. And if we can measure that squeezing, we can say it's not a black hole, it's a neutron star or some object with matter. And so that's something we've been trying to do. And I'll actually talk about some work I've done on that. A lot of people have looked into this. And I'll mention that in the lecture on Wednesday. But we have preliminary, not extremely firm, but weak evidence that we can see the squeezing in 1708-17. And that we can argue there is matter there. And that matter kind of looks like neutron star matter.
I mean, just a quick follow-up. Would it help if you see a gravitational wave associated with a gamma ray burst in some cases and not in the other cases?
Yeah, so that's a fascinating question. That's something I've actually been thinking about quite a bit is, this association with gamma ray bursts and how do we, what do we learn from the association? And in fact, a UChicago student just led a paper where what we did is we asked, you can ask the following question. What is the fraction of short gamma ray, or in other words, what is the fraction of binary neutron stars that we detect that also have short gamma ray bursts? Okay, so far we've detected one confident binary neutron star with no gamma ray burst and one with a gamma ray burst. Okay, and that already gives you some information about the properties of short gamma ray bursts. So for example, the simplest way to think about it is, let's assume that binary neutron stars merge and they emit a short gamma ray burst, but as the picture shows, it only goes, it's a jet, it's very narrow. Okay? The width of that jet tells you how often you actually see the short gamma ray burst. So if the jet is very wide, then every gravitational wave source, because when we measure the gravitational waves, we don't care whether it's pointing at us or not. It's a smaller effect. If every time we see a binary neutron star, we also see a short gamma ray burst, we know the jet is wide. If it's almost never, then we know the jet is very narrow. And you can quantify all that and infer properties of the gamma ray jet from just the ratio, we call it just a counting experiment, just that ratio already is very informative. And then there are all these additional things you can do when you bring in, we have some constraints from the gravitational waves on the inclination, you can do even better. So that's fascinating. And there's a lot of work to do there, but you need a big data set. Mm-hmm. And right now we have a small data set. So that's something for the future. That's an excellent question.
Thank you.